Have you ever really thought about what it takes to do something simple, like reach out and grab a cup of coffee? It feels so automatic, right? But behind the scenes, your brain is performing this incredible symphony of calculations. Today, we're going to pull back that curtain and take a look at the hidden world of how our brain controls movement.
So how does it happen? I mean, really, how do we guide our hand from point A to point B with such incredible precision, without all the wobbling and missing the mark? While the answer lies in this really fascinating partnership between two key managers inside your brain.
Okay, so let's imagine your brain's motor control system is like a company, and it's run by two top executives. One of them is the selector, and their job is to decide which action gets the green light. The other is the fine-tuner, and they're obsessed with making sure that action is executed perfectly. For any movement to feel smooth, these two have to be working together, totally in sync. And here they are, our two managers. On the left, we've got the basal ganglia. This is our movement selector. You can think of it like a gatekeeper. It says yes to the one movement you actually want to make, while at the same time, it's actively shutting down all the other movements you don't want to make. And on the right, we have the cerebellum, our movement fine-tuner. This is the quality control expert, constantly making these tiny real-time adjustments to make sure everything you do is accurate and smooth.
But what happens when one of these managers starts having a bad day? Let's start with the selector. What happens when the basal ganglia, our gatekeeper, starts to fail at its job? Well, the result is something called a resting tremor. This is that rhythmic, involuntary shaking you might see when someone's hand is completely relaxed, just resting in their lap. The key thing is it happens precisely when they aren't trying to move at all. And this is what's so fascinating. The tremor happens at rest because that gatekeeper is failing to block these unwanted signals. But look at that key detail. The tremor often stops when you go to make a voluntary movement. It's like the powerful, intentional command to move just temporarily overrides that faulty, noisy gatekeeper. So at its core, a resting tremor is just noise. It's this cascade of unwanted motor commands that the basal ganglia just can't filter out anymore. It's a faulty signal loop in the brain's circuits, this constant unwanted beat that keeps making it through the broken gate. Okay, so that's our selector. But what about the other manager, the cerebellum? What kind of signal do we get when the fine-tuner starts to glitch out?
This leads to a completely different type of tremor, called an intention tremor. And just like the name suggests, it's basically the opposite of a resting tremor. It only shows up when you intend to do something, like reaching for a door handle or trying to press a button.
And check out the characteristics here. The tremor only happens during movement, but, and this is the really weird part, it actually gets worse the closer the person gets to their target. The whole movement becomes jerky and overshoots the mark, which is a classic telltale sign that the cerebellum, the brain's error correction system, is having problems. This brings us to the core puzzle of this whole thing. I mean, why on earth would a tremor get worse the closer you are to succeeding? It seems totally backward, but the answer is actually found in the physics of a faulty feedback loop.
This is the question, and the answer tells us exactly what the cerebellum is supposed to be doing and what happens when it can't. So first, let's walk through how it's supposed to work. When everything is healthy, you decide to move. Your brain sends the plan to your muscles, but it also sends a copy of that plan to the cerebellum. Then, as you move, the cerebellum is getting this constant stream of feedback about where your hand actually is in space. It acts as a comparator, constantly comparing the plan to reality, and it instantly sends out these tiny correction signals to keep your movement smooth and dead on target. Now, here's what happens when the cerebellum is damaged. The process starts the same, but that crucial compare and correct step gets delayed. The signal is just too slow. So by the time the signal arrives to adjust your hand's position, your hand has already gone past the target. It overshoots. Then your brain sends another correction to pull back, but that signal is also delayed, so you pull back too far. This cycle of overshooting and then overcorrecting creates a wobble, an oscillation, that just gets bigger and more frantic as you try to make those smaller, more precise adjustments right near the target. And right there, that's the aha moment. The tremor isn't random shaking. It's a predictable physical wobble caused by a time delay in the brain's error correction system. It's kind of like trying to steer a car with a huge delay in the steering wheel. You'd just be constantly swerving from one side of the road to the other, trying to correct yourself.
So, as you can see, these two very different tremors aren't just random symptoms. They're actually incredibly specific signals that can help neurologists figure out exactly which part of the brain's complex motor system is in trouble. This chart really lays it all out, side by side. A problem with the basal ganglia, our selector, causes a resting tremor because it's failing to suppress unwanted movements. A problem with the cerebellum, our fine-tuner, causes an intention tremor because it's failing at real-time error correction. For doctors, this is a vital clue because it points them toward completely different underlying conditions. So, the big takeaway here is that a tremor isn't just a symptom, it's a message from the brain. And by carefully looking at when and how it happens, we can actually decode that message and figure out which system is in trouble. Is it the gatekeeper or is it the fine tuner?
Ultimately, the simple act of moving our bodies is this incredible window into the most complex machine in the known universe. And it leaves us with a pretty fascinating question. If tremors can reveal this much, what other secrets about our brain's inner workings are hiding right there in plain sight, just waiting to be revealed by the way we move?